Hi, in this video, I'm going to go through OCR AS-level Chemistry. This is paper 2, and it is the 2019 paper. I'll do the first half of the paper in this video, and the next to the second. Okay, right. First question then. Properties and reactions of group 2 element strontium. The relative atomic mass of strontium can be determined using a mass spectrometer. What is meant by the term relative atomic mass? Okay, so the best way to answer that is with the equation. It is the mass of an average atom divided by the mass of an atom of carbon-12 multiplied by 12. That's the definition you need for that. Okay, right. Right, a sample of strontium has a relative atomic mass of 87.73, and you've got some strontium 88, strontium 87, and one other isotope. Determine the other isotope. So look here, we've got the abundances of these two. So the abundance of the isotope X, let's call it X, is going to be 100 minus those. Okay, so that's going to be 100 minus 100 minus 82.9 and minus 6.9, which is equal to 10.2%. So that's the abundance of X. Okay, now we know that if we the relative atomic mass, the AR, is equal to the abundance of each isotope the sum of the abundance of each isotope multiplied by the mass of each isotope. Right, so they tell us the AR is 87.73. Right, now rather than using percentages here, it's better to use decimals, so that's going to be an abundance of 10.102. Okay, so we fill in that, then we have got the abundance of X is 0.102, and the mass of X is X, plus the abundance of the other one, so that's 0.829 multiplied by 88, the mass of the strontium 88, plus the abundance of the other one, which is 0.069 multiplied by 87. Okay, so let's simplify that. We get 87.73 is equal to 0.102x plus 78.955. Simplify that, we end up with 0.102x is equal to 8.755. Just subtract those two, and then so x is equal to 8.75 divided by 0.102, which gives us 86. Okay, so that is the mass of the other isotope is 86. Okay. Right, physical properties of the element strontium, 5-mark question. Okay. So explain the physical properties of strontium in terms of bonding and structure. Well, strontium is a metal, so we've got a metallic lattice. I need to write that down somewhere. Got a mark for that. What does a metallic lattice look like? Well, you're going to have strontium ions. Now it's going to be a regular lattice of ions. Each one's going to have a 2+ charge because strontium is in group 2, so it loses the 2 valence electrons. So you have a regular arrangement of positive ions, and in between them you have a sea of delocalized electrons. Okay. Okay, so that's our structure and bonding. Now we've got to relate these to the physical properties. Okay, right. First of all, let's do the melting point. Why is the melting point high? Well, it's because you've got a strong attraction. Let's say a strong electrostatic attraction between the strontium ions and the delocalized electrons. Okay, so we say that. That's why it's got a high melting point. Why is the electrical conductivity very good? Well, it's because you've got delocalized electrons. And they can move, and the flow of those electrons is electric current. Okay, so there's that will do you for the 5 marks there. And there's my labeled diagram, which I haven't really labeled, but I've explained what each. So you'd have to say, yeah, these are strontium 2+ ions. The green things are delocalized electrons. Right, the student adds a small amount of strontium to water. So when the reaction is finished, you measure the pH of the final solution. Write the equation for the reaction of strontium with water. So that's a straightforward recall question. So strontium, all the group 2 metals except magnesium will react with cold water in this way, of course. It will give you strontium hydroxide and H2. Now the state symbols, that's solid, liquid. Strontium hydroxide is fairly soluble. Solubility increases with the hydroxide as you go down group 2. So strontium and barium hydroxides both pretty soluble. So aqueous solution and hydrogen gas there. Right. Okay. When the reaction is finished, they don't ask you what the pH there, even though they mentioned the pH in the question, but it would probably be 14 because it's fairly soluble. Right. Okay. Right now, right. Hydrated strontium chloride. Okay, so we've got this, and we've got to do this experiment to find out the value of X, the numbers of water molecules in the hydrated form of the salt, and how they do that. So, well, first of all, they're going to get the hydrated strontium chloride. I'll write an equation down there. They're going to heat that up. So you're going to end up with the anhydrous strontium chloride, and the water will be lost as a gas. Okay, so you're going to get so the important thing to notice there is, look, 1 mole of this stuff gives you 1 mole of the anhydrous stuff, right? So they weigh the empty crucible and they add this, and you're going to find the mass of that by subtraction. They're going to heat this up, and then you're going to, this then will be the anhydrous stuff that will be left over, and again by subtracting the mass of the empty crucible, you can work out the mass of that one. Heat the crucible and residue for another 5 minutes, allow to cool, and weigh the crucible and residue. Repeat the step a further 2 times. They're probably going to ask us that. Okay, so now the first question, the results are here. Okay, we've got to calculate the value of X. I'm just going to copy this equation here. Paste that down there somewhere. Okay, so yeah, so it's 1 mole of the hydrated stuff gives 1 mole of the anhydrous stuff. Okay, so let's do that. Right, so the mass of the hydrated so we're going to do by subtraction, so that's going to be equal to 18.65, that's a crucible with it in there, minus the mass of the empty crucible, 15.96. That gives us 2.69 grams. Let's do the mass of the anhydrous stuff. So that's going to be the mass at the, so that's going to be 17.58. minus 15.96, the empty crucible. That gives us 1.62 grams of the anhydrous stuff. Okay, right, so the first thing we're going to do now is we know that 1 mole of this gives us 1 mole of that, and we're going to try and find out the MR of that. That's what we're going to do, and we know the MR of it. We should then work out the value of X. Now we can't work out the moles of the hydrated stuff because we don't know the MR of it, but we can work out the moles of the anhydrous because we do know the MR of that. So let's do that. Moles of the anhydrous. That's going to be equal to the mass divided by its MR. So we've got 1.62 grams of that, and the MR, well, strontium is 87.6 is the AR of strontium. So the MR of strontium chloride is going to be equal to 158.6. Right, so let's do that, and we get 0.0102. That's the moles of the anhydrous. Now we now know that the moles of the hydrated stuff is the same as that. So let's write that down. So the moles of SrCl2.xH2O is equal to 0.0102, and the MR, so we don't know the MR, sorry, the mass of that stuff, we do know the mass. We worked it out there, 2.69 grams. Now moles is equal to mass over MR. So the MR, we'll just rearrange that. Mass over moles. And if we know the MR, we can work out the value of X in that formula. So the mass is going to be 2.69 divided by 0.0102, which is equal to 263.5. 263.35. Okay. Now, I'll just write down the formula there. So we've got this hydrated salt. We've got SrCl2.xH2O. We know the MR of that bit there. Well, we worked it out. Look, it was 158.6. We know that the MR of the whole thing is 263.35. So the mass of the waters in it, then the XH2O, that's going to be equal to 263.35 minus 158. That gives us 104. And then we've got to find out X, we've got to divide by, well, water has got an MR of 18. So we're going to divide by 18. So X is equal to 104 over 18. And that is equal to 5.83. Okay. Now, it said give our answer to two significant figures. It asks us here, look. So that is going to be X is equal to 5.8. And of course, really, it probably is 6, the real value, because it's always an integer value. But they've asked for two significant figures, so we're going to say 5.8. That is the answer to that question. Okay. Right. Now, suggest why the student takes 4 readings of the mass of the crucible and residue. Right. Why did he repeat it? Okay. Right. The reason why he's doing that, he heated and reweighed, is because he wants to make sure that all the water has been evaporated. Okay. So it's called heating to constant mass. He found that the final mass was, well, first, if you look at his experiments, it said like, it doesn't ask you this, but the first time he did it, he got 17.6 0.61 grams. Then he heated, or 7.6 grams. He heated again, he got 17.61 grams. So he's still obviously losing water at that point. And then he heated it again, he got 17.58 grams. And then again, he did 17.58. So when he gets to this one, because he's got the same number twice, he probably has driven off all the water. Whereas with these ones, you know, the mass is still going down because he hasn't got rid of all the water, right? Suggest two modifications to the method that will reduce the percentage uncertainty in the mass residue. Now, so we're talking about percentage uncertainty, right? What you've got to do is use a larger mass. Okay, if you use a larger mass, then the error is a smaller proportion of that. Or the other thing you could do, of course, is use a balance with greater resolution. So that balance that they used was to the nearest 0.01. Well, gram, you can maybe use a balance to 0.001 gram. Okay. Either of those two ways would increase. Just don't forget, percentage uncertainty is going to be equal to the error over the mass measured. So if you make this number bigger, you make the error smaller. And if you make that number, the error number smaller, then you make the percentage error smaller. So two ways of doing that. Right. Okay. Now on to question about magnesium. Question 2. Right. Magnesium nitrate is used as a fertilizer. The student plans to prepare a solution, 250 centimeters cubed of that concentration, starting from hydrated magnesium nitrate crystals. Describe how the student would prepare the solution, giving full details of quantities, apparatus, and methods. So let's first of all work out do the calculation bit. What mass of magnesium nitrate is he going to use? Okay. We've got to find that out. Right. So we know the we know the volume and we know the concentration required. So we're going to use this equation. We're going to use moles is equal to volume times concentration. Sorry, volume times concentration. Conc times vol. Right, the concentration required is 0.4 and the volume is 250 centimeters cubed. That's 0.25 dm cubed. Convert to dm cubed. That gives us 0.1 mole we need. Right, now we need to work out the mass of magnesium nitrate. So the mass is going to be moles multiplied by the MR. Now, what's the MR of magnesium nitrate? Well, it's going to be 24 for the magnesium, plus we've got 2 nitrogens in there, so 2 times 14. We've got 2 lots of 3, that's 6 oxygens, 6 times 16. And then we've got 6 waters, so that's 6 times 18. That gives us an MR of 256.3. Okay, so the mass then is going to be 0.1 multiplied by 256.3, which is equal to 25.63 grams. That's the mass of magnesium nitrate that we're going to need. Now, describe how the student prepared the solution. Right, so we've got to give the experimental details. Okay, so what we would do is we would weigh right, probably the easiest thing to do is place a beaker on the balance, tear the balance to get 0, and then add directly to the beaker 25 point, not a weighing boat because you're going to leave some in the weighing boat, that many 25.63 grams of magnesium nitrate. Dissolve in about not 250, in about 100 centimeters cubed of water, distilled water. Then you transfer that to a volumetric flask. Transfer to a 250 centimeter cube volumetric. You've got to say a volumetric flask there, you won't get the marks. That's the only piece of apparatus you should use. Volumetric flask is one of those things like that, with a little mark on it at the neck. Okay, now what you've got to do then is rinse the beaker and the stirring rod and transfer the rinsings to the volumetric flask. That makes you've got all of the solid going in there. And then finally, you've got to make up to the mark that I was saying here. Yeah. Add distilled water up to the mark. And finally, stopper and invert the solution. That's all the necessary details there for all of the marks. Okay. Right. Next question then. Right, a solution of magnesium nitrate can be prepared by reacting magnesium carbonate with nitric acid, and the equation is shown below. Calculate the minimum volume in centimeters cubed of nitric acid of that concentration that is needed to prepare a solution containing 5 grams of magnesium nitrate. Okay, so first thing we need to do is work out the number of moles of magnesium nitrate. So let's do that. Moles of magnesium nitrate in 5 grams is equal to the mass over the MR. So that's 5 grams, obviously, and the MR of magnesium nitrate, not the hydrated form. So the MR of magnesium nitrate is 148.3. And that gives us 0.0337 moles of magnesium nitrate. Now we need to work out how much nitric acid is how many moles of nitric acid we need to form that many moles of magnesium nitrate. Well, to form 1 mole of magnesium nitrate, we need 2 moles of nitric acid. Okay, so we're going to say moles nitric acid required is 2 times 0.0337, which is equal to 0.07674 moles. Right. Now we need to work out the volume. Okay, now we know the volume, we know the concentration is that. So we're going to use concentration equals moles over volume. So we'll rearrange to get the volume. Volume is equal to the moles over the concentration. Don't forget that volume is going to be in dm cubed, so we'll have to convert it afterwards. Moles over concentration. That's 0.0674 moles, and the concentration is 1.75 mole per decimeter cubed, which is equal to 0.0385 dm cubed multiplied by 1,000 to get it into centimeters cubed. That gives us 38.5 centimeters cubed. That's the minimum volume, and we've given it to 3 significant figures, so that's right there. Okay. Right, now magnesium nitrate decomposes when heated as shown in the equation. Right. Using oxidation numbers, show which element has been oxidized and which has been reduced when magnesium nitrate decomposes. Okay, so we need to have a look at what's going on here. Okay, now magnesium has oxidation number will not change because in both magnesium in all of its compound is Mg2+, so it's always got an oxidation number of +2, so that's not changing. So we can forget about the magnesium there. So the other 2 elements we need to worry about are the nitrogen and the oxygen. Well, let's look at the oxygen first. Now, oxygen has always got an oxidation number of -2 in its compounds. But of course, its oxidation number as an element is going to be 0. So look here, it's got an oxidation number of -2. And here, well, these ones haven't changed, but these oxygens here, they've gone up to 0. Okay, so when an element's oxidation number goes up, it means it's been oxidized. So the oxygen has been oxidized. So there's something else which is being reduced. It must be the nitrogen. We need to look at that now. Okay, so let's look at the oxidation of nitrogen in magnesium nitrate. Now the easiest thing to do is to think, well, forget about the magnesium. We have a nitrate ion in there, an NO3 single minus. What's the oxidation number of nitrogen there? We're going to use sum of the oxidation numbers is equal to the charge on the species. The charge on the nitrate ion is -1. Now nitrogen we don't know, so let's call that N. Oxygen is always -2, so that's 3 lots of -2, that's -6. Do a little bit of algebra there. So N, take that 6 to the other side, is equal to nitrogen is +5. Okay, so nitrogen's got an oxidation number of +5 there. Whereas in this compound, let's see what the oxidation number is. That's more straightforward. Sum of the oxidation numbers once more is equal to the charge on the species. The charge on the species is 0 in nitrogen dioxide. So we've got N, we've got 2 lots of oxygen, -2 each one, so that's -4. N is equal to +4. So the nitrogen has gone down from +5 to +4. So the nitrogen has been reduced. The oxygen has been oxidized and the nitrogen has been reduced. Okay, right. This question is about 1-iodopentane, which I've drawn down below. Iodopentane can be hydrolyzed by aqueous sodium hydroxide. Outline a mechanism for the reaction. Okay, curly arrows and all dipoles. Right, so we're going to have iodine is more electronegative than carbon, so that's going to be partial negative charge. This is going to be partial positive charge. That's the dipole on that molecule. Right, now we're going to have OH minus. One of the lone pairs on the oxygen, there are 3, we're going to just draw one. That is going to go onto that's a nucleophilic attack, and then the bond between the carbon and the iodine is going to break, so that goes like that. And it says draw the final product. The final product is going to be pentan 1-ol. So that's going to be CH3. I'll draw the last carbon displayed. OH is now stuck on, and H. And the iodine is going to come off as I minus the iodide ion. So include that as well. Okay, that is the mechanism there with all the necessary curly arrows and dipoles shown and products. Right, 1-iodopentane can be hydrolyzed by water using aqueous silver nitrate with ethanol as the solvent. A student uses this method to compare the rate of hydrolysis of iodopentane and 1-bromopentane. What measurement and observation would allow the student to compare the rates of hydrolysis? Well, when you hydrolyze either of those, with the iodopentane, you get I minus produced, and that is going to react with the silver ions in solution to give a precipitate of AgI. Okay, it's a yellow precipitate, so it will go cloudy, and the same will happen with the bromopentane. You get Br minus. You'll get a cream precipitate of AgBr. So you would time how long to go cloudy. Due to the formation of the precipitate. You could make that a bit better by saying time, for example, to obscure a piece of graph paper on the other side of the test tube so you can't see the lines on the graph paper. But time how long it takes to go cloudy due to the formation of a precipitate of the silver halide. For 1 mark, that's enough. 1 iodopentane was found to react faster than 1 bromopentane. What is the reason for that? Right, we need to say, right, that the bond between carbon and iodine is weaker than the bond between carbon and bromine. Okay, so that bond is easier to break, so it reacts faster. That's 2 marks. Just, you might need to say for 2 marks, I haven't looked at the mark scheme, but you might need to say, well, why is this one longer? It's weaker. It's weaker because it is a longer bond, because the iodine atom is bigger. Okay, that's going to be enough for 2 marks, I think. Okay, we've got a mass spectrum of 1 iodopentane. Okay, right, what information is given by the peak labeled 1, this one here, 198. Well, that's the largest peak, the largest. Okay, so that means it hasn't fragmented, so that is equivalent to the molar mass, or the MR, of iodopentane. Or the compound, well, they might not know it's iodopentane, but the compound they're investigating has got an MR of 198. Sometimes you can then work it out. Okay, right, the structural formula of the ions present for the peaks present at Y and Z. Okay, right. Now, so let's think about Y. Let's think about Z first of all. It's 43. Now, you're obviously going to get some kind of fragmentation of the iodopentane molecule. Let's just draw it out. So we're going to get CH3, CH2, CH2, CH2. Okay, now let's have a 43. Well, let's say it fragments. That would weigh, if it fragmented there, CH3 weighs 15. That's weighing obviously not right. If it fragments here, you're going to go end up with that, which weighs C2H5, which is 29, so that's too small. But if it fragments there, then you are going to end up with that, which would have an MR, C3H7. It has got an MR of 43. So that's going to be C3H7. And of course, it's going to be an ion to give a peak. So we need to put a positive charge there. Now, the one at 71, I think we just got to make that. Let's see what happens there. Now, ooh, that should be there. Right, 71. Now, it's not going to be that. That's just going to be 14 bigger, that fragment there. So it's not that. That would be too small. But if we did all of that, you add that up, that is C5H11, and that does have an MR of 71. So basically you get fragmentation there. So C5H11 plus. Again, it's going to be a positive ion, so we need to put that there. Right, now I think that is halfway. Oh no, it's not quite halfway through the paper. We've got another question. 2-iodo-2-methyl butane is an isomer of 1 iodopentane. Draw the structure. Okay. Well, I'll start off. It's methyl butane. We'll draw butane first. So 4 carbons in a row. On carbon atom number 2, 1, 2, 3, 4, we've got a methyl group. So let's put that on there. And we've got an iodine on that one as well. So draw an I there. And then we just need to put our hydrogens elsewhere. That is the isomer. Okay, one similarity and one difference between the mass spectra of 1 iodopentane. Okay, and right. Okay, so the similarities, look at the isomers. So the parent ion, the biggest peak in both of them, the biggest peak is going to have an MZ of 198, because that's the MR of both of those. So that's one similarity. That's what you could also say is if the iodine just drops off, then you will also, this is, you only need to give one, but here's another similarity. You will get a peak with 198 minus 127 for the iodine. You're going to get one of you are going to get one of 71 again. 198 minus 127, that's the mass of iodine. So if the iodine breaks off, you'll get that peak. That's another similarity. One difference. Okay. Right. Now with this one, you can't get this fragment. There's no fragment with an MZ of 43. And remember, that was due to C3H7. You can't get a fragment of that there with it just breaking in one place. Because like, you know, you can get that would be 29. That's not right. If it broke there and there, then yeah, you could get a fragment of 43, but that would have to break in two places. So you can't, with it breaking in one place, you cannot get a fragment of 43. It's impossible. Okay, so that would be one, probably the most obvious difference. And that is halfway. So I'm going to end this video here and continue in the next video.